So we're going to begin our class today. I want to talk a little bit about your computing environment and specifically where you're going to be writing your programs in C++. Before I start that, I know all of you guys are computer science, computer engineering majors. How many of you have experience with C++? Okay, how many people have a lot of C++? Okay, so a little bit. How about a little bit of C++? Okay, how about without the plus plus? How many people have just C? Okay, so nobody, just a few people just C, right? C but not C++, or C and C++? Okay, okay. So how many people have no experience at all with C or C++? Okay, that's fine. You're still in the right place. The most important thing is that you have programming experience and that you guys are smart, willing to work hard, and understand, what we're talking about here. So, obviously it's a programming course, but because it's a graduate course, it's very, very important that you guys get a deep knowledge of this, right? I expect you to come from this class when you finish and become really, really knowledgeable about C++. Like when you go to a company, you should be one of the top 3 people experts in C++ immediately. That's the goal, okay? Because a lot of people, they know a little bit of C++, okay? But they don't really know it. So it's really important to understand how the language works, the power of the language, why it's still important, because it's an old language. The C language was first introduced. Anybody know what year the C language was introduced? You gotta speak really loud because there's a big noiser. Anybody know what year the C language was introduced? Even earlier than that, about 1967. And before the C language, there was another language that preceded C. That language was called B. Really. And that language was developed at AT&T Bell Labs. B for Bell, I don't know. But so after the B language, they decided to improve on the B language, and they came up with a great creative name, C. And so the C language was really developed as the tool to allow the people at AT&T Bell Labs to develop a new operating system. Would you know what it was called? In the late 60s, what operating system was developed at AT&T Bell Labs that we still use today? Unix. Unix. Okay. Unix was an operating system that was built to improve a previous operating system. And that previous operating system was the very first operating system that allowed multi-programming on an operating system, allowed multiple programs to run concurrently on an operating system. Anybody have heard of that operating system before Unix? No, Linux came afterwards, but the system that came before Unix was called Multics, M-U-L-T-I-C-S, Multics. So Multics was improved then with Unix and C language, and essentially most of the code for Unix was written using the C language. So when you're talking about an operating system, right? You're talking about what does an operating system do, basically? What's the purpose of the operating system?
Manages all the applications.
So it manages the applications on the one side, and on the other side, what does it do?
It uses instruction for hardware.
Okay, so it's got to be like an interface between the application layer and the hardware layer. Okay? So for example, if you're talking about accessing a particular port on your computer, that's sort of a hardware responsibility. When you're talking about reading information from an incoming port or incoming card, that's a hardware responsibility. But when you want to read something from a disk, you want to read something from a hard disk, and a disk is a hardware device. Operating system allows you to do that. So it manages all these different hardware devices on the one side, and on the other side, it's able to talk to application programs. So it tries to combine the type of need that all programs are going to need by providing that service for all applications. There's one version and one instance of the operating system running while at the same time, multiple applications are running over that operating system. And that so if you want to write to a disk, and this program wants to write to a disk, and this program, all these programs want to write to a disk, they all have to go through the OS, and OS then basically does the job of giving them access to the disk, managing it. If you want to send something to a printer, operating system. If you didn't have the operating system, you would be required to put all of the logic and software that the operating system does to access hardware devices into every single program. And that's the way it used to be. People used to give instructions to computers, and those instructions included everything from the computer, because the computer was not running anything at all. It was just idle. It wasn't doing anything. It wasn't even running. Then you turn it on, you put the set of instructions, which used to come as a set of cards, and you fed those cards, and you programmed the computer, and some of the routines were operating systems routines. So people say, wait a second, why are we giving the same routines to every single program? We need to have this layer, and this is the operating system, and then C language was written to do that. If you have to communicate to hardware devices, you need to know where they're located, and you need to be able to identify them, and for that we need their what?
Address.
Their address, okay. So that means that the C language had to be able to specify an address of a particular device. Exactly, the address. And the address basically is the single identification of that particular device. So the whole idea of addressing that the C language has comes from the fact that they had to use addresses. They had to refer to specific areas of memory directly. It's called addressing. So and of course, as the language evolved over time, C language became pretty powerful. It was a very powerful language, and some people claim maybe it was not so easy to work with, but compared to the previous languages, it was pretty good. And so the language became very, very popular, not so much even as writing for operating systems, but people adopted the language for all types of computing. All kinds of computing was being done using the C language, which was invented at AT&T Bell Labs by a couple of guys, 2 engineers. Anybody know their names?
Dennis Ritchie and
Brian Kerningham. Very good, okay. And so Kerningham was one guy, Dennis Ritchie was the other guy. Kerningham and Ritchie, they used to call it K&R-C. That's easy to remember, K&R-C. K&R-C means Kerningham and Ritchie C. Not ANSI, not ISO, not like some kind of a big standard, but it was like K&R-C. And they developed the language. The language, I don't know if you've ever seen the original books in the C language. You would expect that the book in the C language would be like this thick because it was so complicated. But actually, K&R came up with a book that was about this thick. The complete book on C. Very, very small. The language was very, very small, but very powerful. You know, so because it's so small, it's easy to make lots of crazy mistakes in the language, of course. And of course, it was still an early language. This language was developed in the late 60s, really matured into the early 70s, and it was a language that was still a procedural language. Because this is way before really the whole idea, the whole notion of object-oriented languages was around. Object-oriented languages didn't even start beginning until right around 1980, and they didn't come into actual use in practice outside of just academic experiments really until the middle 80s. And so right around the middle 80s, early 80s, the C language was then developed into this new paradigm model called the C++ language. And what they wanted to do is they wanted all these great programmers who are already C programmers to use it right away without having to learn a whole new language. So that's good and bad because it's kind of like reverse, kind of backward compatibility. To make it backward compatible, you have to still make it a procedural language, but to make it object-oriented, you have to give it object orientation. Well, how the heck do you do that? I mean, right now you're basically, it's like, are you procedural, are you object-oriented? And C++ said, yeah, we do that. So it was sort of a trade-off that you can do things kind of exactly what you did with C, but then you can do all this whole other stuff. So consequently, all these people who are great C programmers, but did not have the inclination or interest or even maybe even ability to go on to a new paradigm, new model, essentially they say, okay, we'll use C++, but really they were using C concepts, C structure, but they were writing in the C++ language, barely dipping into the new stuff, literally barely dipping into it, if any at all. So in a sense, you can think of the C language sort of as this little universe of stuff, and C++ wanted to embrace all that stuff, so they kind of put a big bubble around it. They took everything pretty much wholesale from C, and they added to it all these different possibilities. And this was quite revolutionary in its day. So people who wanted to embrace the object-oriented parts of C++, they did that. They learned new concepts, they learned new ideas, but it was slow going, and even in industry it was slow going. But the good news is that even if you adopt all of the object orientation of C++, the C language still has a lot of power, and C++ allows you to use all that power. It allows you to use direct addressing. And direct addressing means you can go into a specific memory location and poke that location, get that value out of there, change that value, which is something that languages like Java, languages like C# do not let you go directly into memory. They give you kind of an access to memory, but it's indirect. You don't actually know what the address is. So you have to remember that C++ is going to be much more, it's going to have a lot more manual, you ever drive a manual shift car? Right? So you know when you're in gear 2, you're in gear 2. You can't go 80 miles an hour in gear 2 if you would like to have your car live to another day. Okay? You cannot go 10 miles an hour in gear 5. Right? It's not going to work. You're going to have to find the right gear. So it's a little bit more manual. Your programming will be a little bit more manual. Not terrible, but you have to be careful what you do, because when you write something in C++, because the language is so small and there's so many things you can do with it, when you write something and you switch symbol from here to here, you may be doing something very, very different than you intended. So you have to be aware that you can do some damage with the C++. If you want to get, if you want to make a good computer virus, hey, you probably want to go C. I hope none of you do that, but that's what you want to do because you want to mess around with stuff in places where you shouldn't be messing around. And C lets you do that, whereas other languages are a little bit more protected, a little more safeguarded. Okay, so that's the sort of the big idea. Any questions so far? So, original language is called KNRC, developed at AT&T Bell Labs, and then the next language was developed by a Swedish fellow. Do you remember his name? It's very difficult to pronounce. Bjorn Strustrup. Yeah, that's a spelling test right there. Bjorn Strustrup. And he spelled it B-J-A-R-N-E. Looks like Bjarne. Not Bjorn, B-J-O-R-N. But anyway, Bjorn Strustrup. And he wrote a book. Now, so the KNRC was this thick. Strustrup's book was about this thick. And it's got some scary stuff in there. You open it, it's like, what the heck is that stuff? I mean, you open it up, you get all excited. Like, what's going on here? There's a lot of stuff in that C++. He extended the language a lot. Tried to keep everything that was in there, extended the language, and really did a pretty good job. But because it's more of a manual language, it's up to us, who are the users, to decide how much object-oriented stuff we actually use versus how much do we try to just squeeze in the procedural stuff. Of course, most of the new modern programmers like you guys, the young people, you guys don't even know what procedural programming means. But in some cases, you may have to know if you're going to be using things to write very direct things, device drivers. And of course, a lot of the computer engineers are still using very, very focused, small, routine, small programs that just kind of execute some basic instructions. So we're going to try to cover a lot of that. We're also going to cover some software development concepts, which are known as design patterns. What I've done in the past is I've done a lot of the language, and then I threw the design patterns in. And the reason for that is because design patterns are a very abstract part of C++. And in order to get to the very abstract part of C++, you have to go to some of the more advanced OO parts of C++. In order to get to those parts, you got to be really strong on the basic parts of C++. And so I'm going to try very hard to try to get some of those design patterns earlier than usual, but I don't know how successful I'm going to be. I'm going to try very hard though. Talk about things as they come up. How many of you are very comfortable in designing, for example, a class? A class. How many of you are not so comfortable yet designing a class? Okay, I'm only having a few people voting. So I assume the people who are voting are probably in the latter category, like, ah! Okay, but we're going to talk about that. There's a lot of stuff to talk about before we get to it. Okay, so let's look at your computing environment. How many of you have an environment for C++ already and are ready to go right now for program number 3? Yeah. So not many of you, so we're going to talk about it right now. So we're going to talk about what you need to do to get yourself up and ready so you can start working on programs right away. And I'm going to give you 2 basic options, all right? So let me turn this off, see if I can connect to this. I apologize for this, but somebody went crazy on this thing, and there's no eraser. Sometimes I have an eraser, but I don't have one this time. So give me 1 second, and I'm going to show. And whatever I have here, I will put that stuff available online. But right now, I don't have it online. Okay, so we'll do that. Someplace here, I have this way. Technology has come a long way, but we still have these snakes that are living in the labs. Let's see what we're doing over here. We need to go full wireless here, I think. Let's see how that's going to work out for us. Tell me when you can see it. Can you see it?
No.
Not seeing it. Oh! Nice blue color, right? Wow. I'm going to see if I can get an eraser, because this is very, very bad. IDE, and I'm basically going to give you 2 options that you need to do in order to get yourself going. And so option number 1 is Microsoft Visual Studio. And I will show you where to get it. You will get Microsoft Visual Studio. It's called, the free version is called Community Edition. It's 2017. Okay, and so the link is going to look like this. It says, I think, visualstudio.com/downloads right there, okay? And then when you get that page, you're going to get something that looks like this. And so notice it says free download. Let's make it bigger. I see people straining to see. How's that? Look at that, the power of magnification. So Visual Studio Community, this is Visual Studio Professional. You can get a free trial. You know what that means. Likewise, Enterprise, you can get a free trial. So I just chose to get this one because it'll get the job done very, very well for us. Okay, so Community Edition. When you download that, you're going to get something like this, and you're going to say, you're going to click on it. So this is your click right here. You click over here, and then when it's finished, you finish it. So you're going to say get started. And you can see these are the options that I chose to download on my system. I took the Universal Windows Platform Development for C++, Desktop Development C++, and I just did ASP.NET just for good measure. But you can do more. It's a pretty big download. It'll take a while to do. So as I check off these different boxes, it'll automatically check off over here. You can see what I have. Okay, so once you do that, then it's going to start installing it. You can see mine is starting to install here. And when everything's said and done, I'll go back to it and show you basically what it's going to look like. So the option number 2 is Open Tutorials Point. It's a website, and you can do this anywhere, everywhere. You can actually create an account there. Or if you want to, how many of you have a GitHub account, for example? If you have a GitHub account, you might be able to use your GitHub account to store your projects. And this is an online development environment. This one uses not Microsoft C++, but it uses something called GNU C++, GNU. Okay, so it's called the GNU C++ compiler. So when you go to tutorialspoint.com, you want to go to this icon right here, which says Coding Ground. When you go to Coding Ground, it gives you to this point here. And this is a very long page. It's got lots and lots and lots of stuff. It has probably something close to about 100 different languages and systems that you can train on, including versions of C, C++, I mean, you name it, it's on there. It's a crazy, powerful thing. So we're interested specifically in the C++ compiler, and so I'm going to show you a little bit about both of these two. Just kind of directly go to that online. Okay, so the first thing I'm going to do is, I'm going to show you the Visual C++. That's the Microsoft community version. And I have that right here. I want to show you a little about how that's going to work. I don't care if you understand what my application is doing, it's not important. But basically what I have here is most C++ programs are going to have a few lines like this, pound include. Okay, pound include is very similar to, like in a Java program, you have what? Import, yeah. And how about C#? What do you use? Any C# people? Good. All right. So import. So import is a similar thing. And so basically, you'll know very, very clearly what it means to include something. It has a special meaning here. Then you see there's another statement that says using namespace. Then it has a main method. It's called main. It returns an int. That looks kind of familiar, even if you've never done C++. It's got some crazy stuff in here, which we don't care about. Cout means output. Okay, so it's going to output something. Output what? Hello world. Then it's going to see out something else. It's going to see out something, a string. A string says argc, so it's going to print literally. It's going to print argc. And then it's going to output, this is called the output operator. It's going to output something else. It's going to output the value of argc, which by the way is this parameter right here. So notice that argc is an input parameter coming into main. Then what we're going to do is we're going to loop. And the loop will go from I going from 0, less than argc, increasing by 1. It will output a bracket, the value of I for each loop iteration, a close bracket, an equal sign, and then argv sub I. Argv is this thing right here. We call this an argument vector. And the argument vector is going to be indexed at I. So it's going to give you the value of a string. Argument vector is an array of strings. It will give you the string at index I, as I is changing from 0 to argc. Whatever that means. At the very end, then I'm just simply saying return 0. What is 0? 0 is an int. Since the function is supposed to return an int, I'm returning a 0 because a 0 is as good as any other int, I suppose, right? So that's fine. So let's say we have this. So let's change this a little bit. So instead of little h, we're going to say big H. And I'm going to, instead of saying world, I'm going to say UB with a couple exclamation points. So I made some changes, right? So I have this project, and I'll show you again how to start that. And what I want to do is I want to run this project, so I'll go to the debug icon, and I'm going to either click on this one, or I'm going to click on Control F5. And when I do that, it will compile and run the application in a console window. So it will tell me, you made some changes, the project is out of date, would you like to build it? I'm going to say sure. So I'm going to say yes, and I can opt not to do that in the future. So I'm going to run it. Notice that it says here, hello UB, argc is equal to 1, 0 in brackets is equal to all this, and then it says console application.exe. Press any key to continue. I do that and it disappears. So we are running this program in the IDE, in the environment. Now every program that you're going to compile on your particular local machine is stored someplace. Okay? And so I will show you where the programs are stored. So typically by default you're going to store them under C users, then you're going to be a username. It's going to create a subdirectory called source, and then it's going to create another subdirectory off of source called REPOS, which stands for repository, which is just like a library, a storage, right? Repository. And underneath repository, it's going to give you the name of your project. Under the name of your project, it's going to have a library called, a folder called debug. If I do a directory, dir, in Windows, it will give me a directory listing there, and it shows you dot, which means the current directory, dot dot is the parent directory, and then it has 3 more files here, console application 1 exe, ilk, and pdb. This one right here, this is your executable file. This is your executable file. This is your actual program that's going to run. You can copy this thing onto a floppy drive, on a USB drive, put it on any other machine that's running Windows, run it, and it will run immediately. Okay, it is a running binary linked compiled program. If I want to run it, I can run it also here on command line, and that's important for us to be able to do. I'll show you a little bit about how that works. So for example, so if you get it, look at the directory, how many actual files, not directories, how many files do you see in this directory? 3 files, right? Including the binary executable and a couple of other project files. Okay, so if I want to run this, typically what I'm going to do is I'm going to just type in the name of the program, and the name of the program without the exe is console application. When I run it, let's see what happens here. Notice it says hello UB. It says argc is equal to 1. I'll come back to that. And it says bracket 0 equals console application 1. Okay, let's come back and take a look at what's going on here. Basically, argc, which is called argument count, and argv, which stands for argument vector, are input parameters into main. So when you're running a C++ program, you're allowed to send from the operating system command line parameters into main to give it some startup information that may vary from time to time. And those informations are essentially strings. So it could be a directory location, it could be directory location, it could be somebody's name, it could be a password, it could be a color, it could be a set of names of people, whatever. You can pass those in. So basically what happens is when you run your program, and let's look at it. This is where I ran the program. I typed console application 1. Now console application, if you look at the command line, after I entered on this one, it ran the program. But if you look at this, how many words is this? 1. So the command line includes right now 1 word, and that word is the name of the application program, which is called console application 1. So what happens is the operating system takes the line, the command line, and breaks it up into all of the strings that are on that line. And it differentiates strings by white space. So for example, console application, after I hit enter, that's a white space. So therefore, that's the only thing that's on that line. So therefore, that's the only argument that goes into the argument vector. And it goes into index position 0. So when I'm running the program over here, what I'm saying is since the value of I is equal to 1, because there's only one argument count, and that is the name of the program, then it's indexed at index 0. So when I is 0, argv sub I is the name of the program. Now, if there are going to be other lines on the program, so for example, if I type console application, and then I type in, for example, my last name, then it's clear that the command line has 2 strings. So therefore, argc in the environment will come in as what value? 2. And argv, the array of those strings, will index from 0 to 1. And so when I loop from 0 less than 2, that means 0 and 1, I will print argv sub 0 and argv sub 1, and it will say 0 in brackets, argv sub 0, the value, 1 in brackets, and argv sub 1 in brackets. Let's run it. So when I run this, look what it says over here. Do you see what it did? So it says argc is 2. 1, 2. And likewise, if I do it again and I wanted to add some more, for example, so we'll put Professor Mahmoud here, put Dean Sobe here. Let's even put Alethi. All right. Spell it right. Okay, so you can see over here. So you can see that I'm
5.
so there's 5, but indexed from 0 to 4. Okay? Does that make sense? Okay, so I'm just showing you, now watch this. If I didn't care about those things, I could actually literally take out this stuff right here. I could cut it. I could then go to debug, and I could, or actually go build, and I could rebuild my solution. When I rebuild, doesn't like, okay, now it doesn't like it, right? So what I can do is I can use my clever // techniques, just to slash all this stuff out, because now it's not recognizing it. Okay, let's see if I can rebuild it now. So it says succeeded, 0 failed, 0 skipped. That's a good sign. And then when I run the program, it doesn't matter what I put in over here. Notice it's just going to say this, because I'm basically got rid of all that other stuff. Okay, so that's well and good, and that's the basic stuff. Again, if you understand 5% of the C language stuff, the C++ stuff, that's pretty good. Don't worry about it if you don't understand what this is doing. I'm just trying to show you can do input into main, and everybody knows what a main is, right? So now, let's go to the other side of the coin. So we're going to go to, I showed you guys how to, whoops. So we're going to go here. So this is, remember the development environment, coding ground, right? So this is these are the options. Check it out. So these are online terminals. You can run Python 3, Lua, LPython, Redis, Ruby, you name it. Okay, continues. Algol 68, one of the best languages created out of the 60s that really was the front runner in structured programming. Ancient language. Angular, assembly, you name it. I mean, look at this. You can even run Groovy if you want to, if you're into that kind of thing. All right, Scheme, Smalltalk, Scala, SQLite. Okay, someplace, believe it or not, we also will have C++. So for example, here, this is compiled C++ online, and there are different versions of the compiler. We're going to go to CPP version 11. When you go in here, you basically might get some basic kind of program. And here, notice that I have something called Hello World, right? So if I want to run this one, all I need to do is I need to press the Execute tab or button, and that's going to compile it. The compiling line, which is hard to read, says G++ -std equals C++ 11-o main star.cpp. Now, some of you are not going to know what that means, and that's okay. But at some point in time, you will. And then basically here is main, and main is running this program. This program is compiled, and the executable version of this program is called main. So I'm now running main, and the output of this, of course, is hello world. If I want to change this to, for example, hello UB, like that, okay, then I change it in the source, and I execute. When I execute, it's going to compile it, and notice that the output has been changed. So you can do this, and you can link your code. You can create projects in different places. You can, I believe, you can link it to GitHub. But it's always a nice place to try some standard C++ stuff. Even if you don't have a compiler handy, you can just go online and it works. Okay, you just have to know the links to it. Okay, any questions so far? No questions. All right. So, let's in that case begin talking about C++ language. All right, so this course essentially is object-oriented programming in C++ with design patterns. Anybody know what design patterns are? What are design patterns? Anybody know? Okay, if you don't know, then you're probably in the right class. So that's fine. All right, so let's begin sort of the beginning. What is a C++ program? I think that's a nice place to start, right? So a C++ program, again, because you guys are already experienced programmers, we can talk about concepts that are already familiar to you, even if C++ is not familiar language to you. So a C++ program basically can say it's a set of modules. So a program, one program is composed of multiple pieces, and those pieces we're just going to call those pieces modules. And again, all these notes are going to be available on Canvas. They may already be available, as a matter of fact, because I think I just solved the problem of getting it. So if you look into lectures, you might see this. And so a good question is, what is a module, right? So what is a module? Well, clearly modules make up a program, but a module basically, we can say that it is a program building block. So it's a block, and if you have a few blocks, you can put together a few blocks and you can make a program. So that's basically what a module is. And so the next question is, what exactly makes up a module? What exactly are the pieces or parts of a module? Okay, so a set of statements, but before we even get to that deep level of detail, let's break up a module into two still high-level components. So basically, we're going to say that a C++ module is going to be divided into two pieces. The first pieces will be an H, and the H stands for what? This is important.
Header.
This stands for header. And a header is basically sort of a declaration of functions that will exist, a declaration of classes that may exist. It's a set of headers or prototypes for functions and classes. That's what an H is. So it declares what is in the module, but it does not do what?
Execute.
Somebody said it.
Implement.
It does not implement. It declares, it says, these are in the module, but it doesn't actually make them so. So, the second part of the module, we're going to say .cpp, and this is basically, and I'm using dot because these are standard type extensions that you're going to see. So .cpp is the implementation of the module, and H is the header of the module. You need both to make a module, but they are one module. But we split them out, and there are huge advantages to taking this module and splitting its implementation and its declaration. Okay? What exactly is a function header or a function prototype? What does that mean? What is a function header or prototype? Anybody?
Defines
So what does the header or prototype contain?
Declarations,
Like, what does it declare?
like integer, number, string, like this.
Okay, but if I have a header, what might I find in a header?
Libraries.
Maybe the name of a function or routine, maybe the name of a class, maybe some of the methods. What will I not find there? Implementation. Where's implementation? Right here. So declaration says what things are going to be, but doesn't do them. So if you think of a function that calculates, for example, let's say we want to have a function that takes 3 parameters and returns, let's say, the sum of the 3 numbers. So that function would, let's say it's taking an integer and another integer and another integer and returning the sum of those integers. So we would say the function, maybe a good name for this would be sum, the return type would be an int, and the 3 parameters would be int, int, int. And then we would have parentheses around int, 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 because they're parameters, and then we would put a semicolon, and we're done. That's a declaration. The declaration says there will be a function called sum with 3 ints returning an int. If the declaration says print, open close parentheses, void, it says there will be a function called print, which will take no parameters and return nothing. Okay? So declaration can declare headers of functions. So after the parentheses, we just put a semicolon and we're done. Now, this function, of course, has to be brought to life in the implementation, where the header, again, will be replicated, but now code will be provided. if you think about it, the header is like a what into the module? Like a what? Almost.
I mean, it defines the API sort of.
What is it?
Interface.
Like an interface. So for example, if I have a header, and the header says there's a function sum, int, returning an int, I can call this function based on the header without having knowledge about how that function is implemented. Just knowing the function exists. Does that make sense? So if module 1, header, CPP, if it has a function called sum, int, returning an int, and then I have module 2, and module 2 needs to use the sum, there's no reason why module 2 can't call sum based upon its header before it's actually been written. Because if I show you that it's returning an int and takes int as parameters, and I call it by saying sum 3, 5, 8, assign it into int j, then I'm calling it correctly based upon the interface. So as long as the header file has been created, another module can call those functions, and the compiler says it looks like you're calling those functions correctly, and compile them successfully, even though the function itself hasn't been coded. Does that make sense? I like that way. They said the. You guys can still see, right? We don't want to make it too sleepy. Everybody getting ready for dinner, thinking about what they want on their pizza. I know. All right. So let's talk about what is a compiler. Now, what is a compiler? What's another word for compiler? Kind of, is similar, but in general, starts with T-R-A. Translator. So a compiler is a translator. It translates one version of something into another version of something. Question?
High-level language to low-level.
Yes, that's good. Well, usually a compiler, it doesn't have to go high level to low level. You get a compiler that goes from Java to C#. So a compiler is basically a translator. It could be doing a lot of different things. Then we have something called a linker. How many of you have heard of a linker? Okay, a lot of you probably haven't heard of that. What the heck is a linker? Well, here's what a linker is. So a compiler, essentially, remember what I said a C++ program was? It's a collection of modules. So you have a module. Let's say you have 4 of them. And of course, every module is right, split into 2 pieces. That's cool. Okay, so the idea is, I'm going to develop a program with 3 of my best friends. This guy right here, this guy right here, and this guy right here. Should have a lady in there, but next time. So these 3 guys and me, we're going to develop a program. And we decided that probably we want to do about equal work, and the program requires about 4 equal modules. So what we do is we sit down and we design how the program is going to work. We say, hey, this module is going to do this module is going to do that, my module is going to do this, and his module is going to do that. Okay. And then we decide about the header for each of those modules. Well, we're going to have to find standard deviation of some real numbers, so we're going to take an array of reals, and we're going to return a real. That's going to give us standard deviation. So we need an array of real numbers, like floats, and return, let's say, a double or something like that. And we're going to do it for every single function within the module. So I'm going to have a bunch of functions. Everybody's going to have a bunch of functions. When we finish our 4-hour meeting, we will have the header files pretty much defined. We will not have implemented any of them, but we have them defined. So now what I'm going to do is I'm going to write my functions. Because I have maybe 10 functions to write. He's got 10, he's got 9, he's got 7. And I write my functions, but my functions, again, the reason you have modularity in a program is so one module can use the services of another one. So I need the services of his module. I have the header for him, but I don't have the code. I don't need the code. I'm going to call in my code his functions as if they existed. And the compiler has to say, that looks good. You're calling it correctly. You're calling it with the right parameters, and you're doing the right thing with the return value. Good job. But there's no code. So if I can't run my module, because my module can be satisfied that I'm writing it syntactically correctly, but I can't run it because his code doesn't exist, neither does his or his, right? We're in parallel designing our own code off the headers that we've agreed upon. But what I want to be able to do is I want to write all my 10 functions, call modules from all these guys that are creating them, and compile them using the C++ compiler to make sure the syntax of my code is strong, is correct. And I can do that, but I can't run it, which means I will not come out with an executable module. But I will come out with a binary version of my code, compiled, and says it looks good. Well, as I'm doing that, so is he, so is he, so is he. So basically, we get together 4 days later, and 4 days later, we all have our compiled successfully modules. So now what we want to do is we want to draw the lines between them and have them start talking to each other. So we want to do what with those modules? We want to link them. And linking is a way of saying, when I called sum, now I'm going to provide you the module that has a defined link to it. That means when that function is called, I want you to call that function. What does that mean? Well, that function is going to sit someplace in memory. So that means when you call that function, I want you to jump to that address. Linking is a way of finding the addresses of where the functions that we've been calling are actually going to be. That is what a linker is, amongst other things. We'll get into more what a linker does. So a linker is a way to resolve addresses of functions. It's also a way to say, hey, that function doesn't exist. I'm not linking it. You got a linker error. You put a function sum in there in your header. I called sum. I compiled it against the header that I included. #include. Then I put his module and my modules together, and when I tried to link them, it tried to find the definition, the implementation, the definition of sum, and it didn't find it. Okay, so let me tell you a little bit more about what a compiler does. So a compiler, of course, has to compile the syntax to make sure that what you're writing is legal in C++. If it's standard C++, it's easy to check. If you're calling your own function within your own module, it's easy to check. If you're calling a function which is in his module, or his module, or his module, then it goes to the header to make sure the header agrees with the call. And if it does, then it's fine. You can still, so I can create an object module by compiling my module along with these guys' headers. So my CPP becomes an OBJ. What's OBJ? Binary version of my code. Binary. Compiled, really. Not runnable, because it has to be linked with the other modules to be a runnable program, but it is compiled successfully. So, what does the compiler have to add to this OBJ so that the linker can do its job? Well, let's think of it this way. If I'm calling sum, and it's in the header from him, but he doesn't define it, then the linker has to say, okay, you need sum, you're advertising it, but you're not providing it. Linker error. Or perhaps what happens is he does provide it, but instead of saying int returns int, he says int string returns void. Then it's going to say, well, I found sum, but it ain't matching what you're doing here. That's not going to work. Those are not compatible. You call this, and this header is different than that header. That's a problem here. Right? That's a problem. Or he does define it and perfectly, but by accident he forgot that this guy's doing sum. He does sum too. He puts it into his header. He defines it again. So now I have two modules that have correctly defined sum, but now the linker says, okay, I want sum, and both these guys are giving it to me. I don't know, the linker error. It's defined more than once. Not good. So what happens is, when you compile a module, there are three things that module, that OBJ gets when it compiles successfully. By the way, this is called separate compilation. Separate compilation. Separate compilation means we are separately compiling each module before any kind of linking goes into effect. Separately compiling each module. So, three things are part of every compile. Take it back. Three things are part of every successful compile. So we have our source. We'll call it CPP, right? That's this definition part of the module. That's the part. We compile the CPP. We actually don't even compile the H. Try to compile the H. Sorry. So now the CPP is the source. So now we're going through the compiling process. And of course, if we're doing something wrong, the compiler will give us errors. We go back and try to fix it. Eventually, we get a clean compile. And the result will be a .obj. If you're in Unix, it might be just called .o. O for object. Source, object. But in addition to these two things, the compiler also generates two lists as part of this compiled module, and that is the imports and the exports. So the compiler generates two lists as part of the, so the OBJ file contains the object code, which is the binary code of your module, checked for syntax, and a list of exports and imports. Now, what are exports? Exports are anything you, that means this module define. So exports are anything you define. If you're defining a function, that's an export. If you're defining a class with methods, that's an export. Anything you define is an export. It's part of the OBJ. The imports are anything you use from another module. So what happens is, if I have a C++ program, and the C++ program is made out of 4 modules, 1, 2, 3, 4, then I will get 4 object files, right? Each of them will have an export list and an import list. Export, import. By the way, these export and import lists, you are not going to see them on your disk. They are embedded, literally, figuratively, embedded within the OBJ file. Just like your picture of your favorite artist is embedded in your MP3 file. It's inside the file. So are these things. So now, so basically the compiler will do all this stuff. The compiler will get you to this point, and now we need to have a linker, right? So the linker will then look at every single import list for every single module and make sure what? That there is another module which which
Same.
exports it. And exactly one module and not two modules. And make sure that those declarations, the headers, agree with what they're supposed to be. Remember, because compiling doesn't check against the actual version, it checks against some header file. So as long as the header file hasn't been modified and implemented correctly by its own compiler, everything's good to go. Now, so every import has to be satisfied by exactly one export that's part of the linker. And everything you define has to be an export. So if you have a function called ABC or a class called ABC, and that means I'm exporting ABC. But if this guy has a class called ABC and is exporting ABC, that also could be a clash. Because you can't have two of the same classes being exported by two different modules. Because then which one am I going to use when somebody from a third module refers to this module name? You understand what I'm saying? So we have to have an unequivocal, without any conflict, selection of one-to-one correspondence of imports to exports. Has to be unambiguous. You know what I mean by ambiguous? Unambiguous means it has to be crystal clear. All right? Like, for example, crystal clear would be like, which guy in the class are you talking about? The guy in the hat. Okay, 3 guys in hats, 4 guys in hats. That's not ambiguous. That's ambiguous. We don't know what you're talking about. So it has to be unambiguous. Okay. So that is what a linker does. A linker basically does all the resolution of the import-export stuff. And then finally, when the linker has been satisfied, your program becomes linked and now has to be loaded. A loaded program is loaded into memory, ready to run, to execute. And in order to run, when a function is called, it has to be at a particular address. Not some general address, some particular address. Because when his module goes in right here, it is at address 2000. And his function sum is 500 bytes away from the beginning. That's 2000 plus 500 is 2500. So when I call sum, when I'm loaded into memory, I'm calling address 2500 today. But tomorrow, when I load the program, it's going to go to a different location possibly. So his module will not go at address 2000, it might go at address 75,000. But the offset to that function is still going to be 500, so it's probably going to be 75,500. So so the loader has to basically load addresses right now in memory that need to be called when a function is calling a particular value. So that's what a loader does. It basically now makes a final location. Once we do that, we're ready to run. Once we load the program into memory, we just type in
main application mode, hello world.
and it runs very, very nicely. Okay, I think it's a good time to stop. This is kind of what the class is going to be like. All right, so these notes will be available. I suggest that you guys always look a little bit ahead in the notes. I'm always going to cover the notes, but if you see kind of what's coming up ahead, there are on the syllabus 2 recommended textbooks. They're not required by a highly recommended. They're old, they're cheap, they're great. There are 2 of them. One is by a guy named Johnsonbaugh, and another one is by a guy named Wang. And they're both really, really good. Really, really good C++ books. I use a little bit of some of the Wang stuff in there, but C++ hasn't changed for a very long time. So we don't need to update the books like Java. You know, Java, every year there's a new Java. Okay, that's old. Nobody uses that anymore. Nobody uses that old 2017 stuff. It's old hat. We've moved on. C++ is pretty much there. So you can get these books. So the books I put on the syllabus, you can get them very cheaply. I mean, probably like less than $5. Go someplace, get them quickly. They're fantastic reference books. I'm not going to assign anything directly from those books, but they're fantastic reference books. The Johnson Bow book is a little bit easier, still good, and the Wang book is a little bit more in depth, but they're both a heck of a lot easier than the Struster book, which is like crazy. I'll bring it in sometimes so you can kind of look at it as like, wow. Now, if I brought it in today, you might quit the class. But if I bring it at the end of the semester, like, yeah, I get most of this stuff. That's all you can hope to do. All right, see you guys next time.